Okay, so hello and welcome back. So in this video we want to basically talk a little bit about the next part, which we have here as precision of measuring tools and significant figures. Okay, so let's go through the text once so that we know what we are dealing with, and then we will go back if necessary and explain a couple of things and then we will take it from there. So an important factor in the accuracy and precision of measurements involves the precision of the measuring tool. Of course, the precision of the measuring tool is important because otherwise you wouldn't get any precision, right? And in general, a precise measuring tool is one that can measure values in very small increments. For example, a standard ruler can measure length to the nearest millimeter, while a caliper can measure length to the nearest hundredth of a millimeter, meaning that not 1/10 but 100th of a millimeter. This caliper is a more precise measuring tool because it can measure extremely small differences in length. The more precise the measuring tool, the more precise and accurate the measurement can be. Of course, can be, not will be. You need to pay attention to the wording here, which is of course important. The more precise the measuring tool, the more precise and accurate the measurement can be, which is of course correct. When we express measured values, we can only list as many digits as we initially measured with our measuring tool. For example, if you use a standard ruler to measure the length of a stick, you may measure it to be 36.7 centimeters. Now I have actually read this part before, and I think what is meant here is that, what is assumed here is that a standard ruler, what is meant by a standard ruler, I think this ruler can measure only to the nearest centimeter, not to the nearest millimeter, for the reason that I'm going to tell you right now. In just a few moments. For example, if you use a standard ruler to measure the length of a stick, you may measure it to be 36.7 centimeter. You could not express this value as 36.71 centimeter because your measuring tool was not precise enough to measure 100th of a centimeter. It should be noted that the last digit in a measured value has been estimated in some way by the person performing the measurement. This is of course important, and it should be of course noted. For example, the person measuring the length of a stick with a ruler notices that the stick length seems to be somewhere in between 36.6 and 36.7 centimeter. Now this doesn't make much sense. I think they have made a mistake here, and I'm going to tell you why. So let me go over this sentence again. It says that for example, the person measuring the length of a stick with a ruler notices that the stick length seems to be somewhere in between 36.6 centimeter and 36.7 centimeter. That means that this ruler is actually graduated all the way up to, it can basically actually measure all to the nearest millimeter, right? So if it can measure to the nearest millimeter, then of course you would be able to report your measurement, the result of your measurement, even to 100th of a centimeter, because you could already measure all the way up to 1/10 of a centimeter. So then the 100th of a centimeter would be, of course, approximation, but still you could do it, right? Because you can see that the length of the stick is somewhere between 36.6 and 36.7 centimeter. So then you would say that it's either 36.61, 36.62, or 36.6, for example, 3, and so on and so forth, all the way up to 36.7, right? So, and he or she must estimate the value of the last digit. Using the method of significant figures, the rule is that the last digit written down in a measurement is the first digit with some uncertainty. Which is, of course, I will talk about this. It's not the best statement that you could write, but well, I know what they mean, hopefully. In order to determine the number of significant digits in a value, start with the first measured value at the left and count the number of digits through the last digit written on the right. For example, the measured value 36.7 centimeter has 3 digits or 3 significant figures. Significant figures indicate the precision of a measuring tool that was used to measure a value. Okay, so we need to talk a little bit about this because there is some errors in there. I mean, you would normally get confused by this if you paid enough attention to the text. Now, there is one thing here, they talk about zeros, so special consideration is given to zeros when counting significant figures. The zeros in 0.053 are not significant. Of course, these are not significant, and I'll tell you why. Because they are only placekeepers that locate the decimal point. There are 2 significant figures in this number. The zeros in 10.053 are not placekeepers but are significant. This number has 5 significant figures. The zeros in 1300 may or may not be significant depending on the style of writing numbers, right? Otherwise, you should basically, of course, follow some sort of style, and you need to indicate in your writing. For example, if you're writing a book, you need to let others know how you write your numbers. For example, 1300 normally, in 1300 normally the 2 zeros are not significant unless you meant the zeros actually to be significant, right? And in case what I'm saying doesn't make any sense to you, we will talk about them right in a few moments once we have gone through the text a little bit. So they could mean the number is known to, so the zeros in 1300 may or may not be significant depending on the style of writing numbers. They could mean the number is known to the last digit, or they could be placekeepers. So 1300 could have 2, 3, or 4 significant figures. And to avoid this ambiguity, write 1300 in scientific notation. Zeros are significant except when they serve only as placekeepers. Now, the next thing that we have here is check your understanding. We will go through this later because I need to first explain all of these parts, and then we will go through this part. And then we have significant figures in calculations. So when combining measurements with different degrees of measurements with different degrees of accuracy and precision, the number of significant digits in the final answer can be no greater than the number of significant digits in the least precise measured value. Okay, there are 2 different rules, one for multiplication and division and other for addition and subtraction, as discussed below. Rule number 1, we have for multiplication and division, the result should have the same number of significant figures as the quantity having the least significant figures entering into the calculation. For example, the area of a circle can be calculated from its radius using a is equal to pi r squared. Let us see how many significant figures the area has if the radius has only 2. Say, for example, r is equal to 1.2 meters. So let's say that basically 1 and 2 are significant, which they are. And if that is the case, then a is equal to pi r squared is equal to 3.1415, and so you can just keep going with pi. And then you have 1.2 meters squared, which gives you some number like 4.5238934 square meters. Is what you would get using a calculator that has an 8-digit output. But because the radius has only 2 significant figures, it limits the calculated quantity to 2 significant figures, or basically you would have to round to 5 here, which gives you 4.5 square meters. Even though pi is good to at least 8 digits. Your pi was 2, 4, and 6, and you had 8 digits for pi, but well, over here the number of significant figures in the radius itself only had 2 significant figures, so that's basically the number of significant figures that you get. And remember that here we are actually raising this number to the 2nd power as well, but still we are keeping the same number of significant figures that the original number has. And for rule number 2, we have for addition and subtraction, so the answer can contain no more decimal places than the least precise measurement. So for addition and subtraction, the answer can contain no more decimal places than the least precise measurement. So this is not talking about the significant figures or anything like that. It's talking about precision, which is basically, precision means that you are, it's all about the number of decimal places that you have after the decimal point, of course. So suppose that you buy 7.56 kilograms of potatoes in a grocery store, as measured with a scale with precision 0.01 kilogram, right? So then you drop off 6.052 kilogram of potatoes at your laboratory as measured by a scale with precision 0.01 kilogram. Finally, you go home and add 13.7 kilogram of potatoes as measured by a bathroom scale with precision 0.1 kilogram. How many kilograms of potatoes do you now have, and how many significant figures are appropriate in the answer? The mass is found by simply addition and subtraction, right? So in this case also we have this calculation here, which we will go through in just a few moments once we are done with the text. Next, we identify the least precise measurement, which is 13.7 kilogram. This measurement is expressed to the 0.1 decimal place, so our final answer must also be expressed to the 0.1 decimal place. Thus, the answer is rounded to the 10th place, giving us 15.2 kilograms, right? So now we have some part over here as well, which is about significant figures in this text, which seems to be some sort of agreement that they have provided here, or some sort of I don't know, convention that they have kept throughout this text, which is of course always a good thing to know once you're reading a text. One thing that you need to know is basically their notation and the way that they write their numbers. Those two things are very important, otherwise you wouldn't understand exactly what they meant by what they wrote, right? So significant figures in this text. In this text, most numbers are assumed to have 3 significant figures, which is not a very good statement. Furthermore, consistent numbers of significant figures are used in all worked examples. Consistent numbers of significant figures are used in all worked examples. You will note that an answer given to 3 digits is based on input good to at least 3 digits. For example, you will note that an answer given to 3 digits is based on input good to at least 3 digits. For example, I didn't understand this part. If the input, I kind of did, but well, kind of also I did not. If the input has fewer significant figures, the answer will also have fewer significant figures. Care is also taken that the number of significant figures is reasonable for the situation posed. In some topics, particularly in optics, some accurate numbers are needed and more than 3 significant figures will be used. Finally, if a number is exact, such as the 2 in the formula for the circumference of a circle, c is equal to 2 pi r, it does not affect the number of significant figures in the calculation, which is of course true, meaning that, well, we will talk about that as well. And there is one example here that we can go through as well, and then we have this part which is about PHET, explorations estimation, explores size estimation in 1, 2, and 3 dimensions. Multiple levels of difficulty allow for progressive skill improvement. This media is not supporting this reader, and then you have to open it in a browser where you can, I think it needs Flash to basically show you the contents of this basically, what do you call it, visualization or I don't know. Now they call it I don't remember the word really right now. Now, let's now go through let me actually talk to you a little bit about the text that we have here, and then we will keep moving. This part is actually very, very important. So the first part that we have here says that an important factor in the accuracy and precision of measurements involves the precision of the measuring tool. Of course, that's true. In general, a precise measuring tool is one that can measure values in very small increments. So when we say a precise measuring tool, what that means is that, well, we talked about the concept of precision, and we said that basically precision means that basically when you say that the measurement is precise, what that means is that, for example, let me give you an example here. When we say that a measurement is precise, we talked about, for example, this example over here, and we said that this measurement was accurate because all of these measurements, all of these attempts of the GPS system to locate the restaurant which we assumed was at the bull's eye, all of these basically measurements are pretty close to the actual location of the restaurant in the center of the circle. But as you can see, the different basically black dots are far apart from one another, and that denotes low precision, right? That shows low precision because if you think of this in terms of a number line, what you would get is that suppose that you got, for example, the actual value of suppose you got the actual location of the restaurant over here, and you can assign some number to this point on this number line, and you would get, for example, and then what happens is that you would I mean, one of your measurements is right here, one of your measurements is right here, and one of your measurements is probably right here, and one of your measurements is probably right here. So what that means is that you see the distance between these two measurements is this much distance between these two measurements on the number line, or there is basically this much distance between these two measurements on the number line, or there is, and so on and so forth, between these two measurements, and so on and so forth. So, but on the other hand, if you had some other measurement system in which, for example, you got basically all of these measurements here, you can see that there is only this much distance between these two measurements, or between these two measurements there is actually probably no distance. Between these two measurements there is probably no distance. So all of them are very close together. So that means that this precision was very, very precise. Of course, relatively very precise, right? Now this is one thing that we talked about. Another thing that we talked about was basically the concept of precision, basically precise measuring tools. That is a slightly different concept, as I can see it. So basically a precise measuring tool is one that basically that can measure values in very small increments. What that means is that basically, for example, suppose that you have a voltmeter, right? You have a digital voltmeter. Now this digital voltmeter, it usually has a screen, and on this screen you have some sort of display, and then you have a bunch of numbers over here. Now what happens is that basically the more digits that you have on your display, and the more precise that the digital voltmeter is, basically the more you can sense the difference between voltages between voltage changes in small increments. Meaning that, for example, suppose that I have a voltage of I have a power supply, and on this power supply I have basically all of these and I have all of these, basically these are my outputs, and these are some controls, everything, and so on and so forth. Now normally a power supply has a knob over here, which is a potentiometer. When you turn this potentiometer, your output, for example, suppose that you have only one channel on your, or one rail or one output on your power supply, and then your output would be on these two basically posts on your power supply. and then you have this knob over here, and you can turn it, and then this voltage, the voltage on the output of the power supply is changed. Now normally, I mean, for the purposes of a simple electronics lab, you don't need that much precision. So when you turn this knob, for example, the voltage changes from for example, it changes from 12 volts all of a sudden, for example, to 12.2 volts, meaning that by moving this, like, for it very slightly, just barely touching it, the voltage jumps up or down all of a sudden by 0.2 volts, right? Now, in some situations, this kind of power supply is just simply not acceptable, because you want to have control over your voltage, meaning that you want to basically be able to adjust your voltage all the way up to 1,000th of a volt, meaning that you want to be able to adjust your voltage exactly to 12.002 volts, right? So now let's suppose that in this situation, our power supply is actually capable of doing this, and I need to point out that this sort of power supply would cost a lot of money, probably at least $1,000, $2,000 or so. Now you have this power supply, and you connect your power supply to and this is your voltmeter, of course, and there is 2 posts down here that is connected to your circuit, or whatever it is that you're measuring. And so these wires are connected here. So now the output of your power supply is connected to your voltmeter, and you can read the output voltage of the power supply on your voltmeter, right? Now, on this power supply, I can change my voltage from, for example, 12.002 volts. I can change it to 12.004 volts. I can do that here. I have no problem with that. But then, whether I can see the difference of 0.002 of a volt change in the voltage here on my multimeter or digital voltmeter, that's a completely different thing, because that's a completely different matter, because then this voltmeter must also be able to show that on meaning that it's supposed to actually be able to sense that sort of slight change in the voltage and be able to actually show that on the screen here, right? So the smaller these increments and the harder it's going to be for the voltmeter to actually sense them and show them on the screen here. So basically, the more that this digital voltmeter can show these smaller and smaller increments in the voltage, for example, or in resistance, or whatever it is that it measures, the more precise your voltmeter is said to be, right? So what that means is that so therefore we say that the precise measuring tool is one that can measure values in very small increments, and that's the meaning of that, right? Now let's see what we have next here. Okay, so then basically the rest of the material that we have here we have, so we said that basically in general, a precise measuring tool is one that can measure values in very small increments. For example, a standard ruler can measure length to the nearest millimeter, while a caliper can measure length to the nearest hundredth of a millimeter. So the caliper is a more precise measuring tool because it can measure extremely small differences in length. Now, the more precise the measuring tool, the more precise and accurate the measurement can be. Okay? Now, when we express measured values, we can only list as many digits as we initially measured with our measuring tool. For example, if you use a standard ruler to measure the length of a stick, you may measure it to 36.7 centimeters. You could not express this value as 36.71 centimeter because your measuring tool was not precise enough to measure a hundredth of a centimeter. It should be noted that the last digit in a measured value has been estimated in some way. Now, in order to understand this concept, let us basically measure a stick using a ruler, right? So suppose that you have a standard ruler here, something like this, and in your standard ruler you have all of these basically your measurement, your graduations start from here. So let's say that you have for example, this is 1 centimeter. This is, for example, 2, 3, 4, and 5, and 6 centimeter, right? And you can just keep going. So this is 2 centimeter, this is 3 centimeter, this is 4 centimeter, this is 5 centimeter, and this is 6 centimeter. Now you know that on a standard ruler, what happens is that you can measure all the way up to 1 millimeter, meaning that basically this is 5 millimeter, and then each of these distances is divided into 5 equal distances, meaning that you get 1, 2, 3, and 4, and 1, 2, 3, and 4. So you have basically 1, 2, 3, and 4. So 1, 2, 3, 4, and 5 equal distances here, and you have 1, 2, 3, 4, so 5 equal distances here, and then you have 1 centimeter, right? And the same thing again keeps happening here, and so on and so forth. So that's how a standard ruler works, and these graduations are repeated all throughout your ruler. Now suppose that I put the stick basically point end to end across my ruler, and suppose that the ruler that the stick comes all the way up to here, right? The stick comes all the way up to here. Now I need to read this length on my ruler, right? And remember that my ruler basically measures all the way up to 1 millimeter. Above 1 millimeter, more precise than 1 millimeter is not possible for me on this ruler, because it's not been graduated to a precision higher than 1 millimeter. Now what I can do here, of course, between 4 and 5 centimeters, so now I know that basically the length of this stick is somewhere between 4 and 5 centimeters. But the good news is that I can still measure more precisely, because my ruler has been graduated to millimeters as well, meaning that I get 1, and that I get basically 1, 2, 3, and 4 here, and 1, 2, 3, and 4 here. So that means that this is 4 centimeter, this is 5 centimeter, and this is this marking over here. This marking over here is actually, let's say that this is 4.4 centimeter. This marking over here is 4.5 4.5 centimeter, right? And let's assume that that the edge of the stick is somewhere between 4.4 and 4.5 centimeter. If I denote the length of the stick as A, for example, the length of the stick as, take it A, for example, then I can say that A is some value between 4.4 and 4.5, and the unit is centimeter. So 4.4 centimeter and 4.5 centimeter. Now, so as you can see, if I basically the digits that I have here, these two digits are of course certain digits, meaning that I have not estimated in any way, because I can read them on my graduations, right? And this is kind of a little bit different from what has been said in the text. The text might be a little bit confused here. I mean, the person that has written this part of the text might have made some sort of logical mistake, or might have been making other assumptions. I don't know what the problem has been, but it doesn't make any it doesn't make any logical sense really. So these two digits, for example 4.4, they have no uncertainty. They are completely certain. I'm completely certain of the fact that 4.4 centimeter and 4.5 centimeter, the length of the stick is somewhere between these two values, because I can see them on my ruler, right? Now, since I can see them on my ruler, I can say that basically, based on this, I can say that the length of the stick is either, for example, 4.1 centimeter, 4.4. Sorry, the length of the stick is 4.41 centimeter, or you can say that it's 4.42 centimeter, or you can say that it's 4.3 centimeter, all the way up to 4. Let's call it 4.49 centimeter, right? Now, in all of these measurements, as you can see, I have 1/100th of a centimeter as well, here, 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 and here. And, well, of course, because 1/100th of a centimeter is not graduated here, these digits have an uncertainty. These digits are actually uncertain. But I have to make an estimation here, meaning that I'm going to say that, for example, because the edge of the stick is very close to 4.4 centimeter, I'm going to go with 4.42 centimeter, right? So I'm going to report the result of this measurement as A is equal to 4.42 centimeter, and I know that this digit here, 4, this contains uncertainty. This contains uncertainty because the ruler has been graduated only to a 1/100th of 1/10th of 1/10 centimeter. 1/10 centimeter, right? And this is 1/100th of a centimeter, so there is uncertainty there. Now it's a convention in physics that whenever you measure something, you measure it this way, exactly using the same basically exactly following the same procedure, and then you report your values as you report your value as a is equal to 4.42 centimeter, and it's understood by everybody that basically this digit has uncertainty. This digit is uncertain, and moreover, considering the whole situation and the whole configuration of this situation, I call these these three digits. Basically, I can say that this number has three significant figures. When you want to count the number of significant figures, you have to start from the far left and count all the way to the digit which basically has uncertainty, meaning that the digit that has uncertainty is also counted as one of the significant figures, and then that way you get basically three significant figures for this number, right? And so basically it makes sense that basically in the text we have basically in this part over here it says that he or she must estimate the value of the last digit. So that is the meaning of that. So using the method of significant figures, the rule is that the last digit written down in a measurement is the first digit with some uncertainty, which is what we saw what that means. Now, in order to determine the last digit written on the right, in order to determine the number of significant digits in a value, start with the first measured value at the left and count the number of digits through the last digit written on the right. For example, the measured value 36.7 centimeter has three digits or significant figures. Significant figures indicate the precision of a measuring tool that was used to measure a value. And well, this is a kind of a well, if you understand how the decimal number works, you already understand Now let me read through this part as well. Actually, I don't want to get into any other books. Now, special consideration is given to zeros when counting significant figures. So, for example, let's say that you have this number over here. I want to make it simple as possible, because otherwise we would get into trouble. So, for example, let's say that you've made some measurement and you have reported the value of this measurement as 0.053, and the unit is whatever it is, it doesn't really matter. So what that means is that, for example, or let me start this way, right? Let me start this way. So let's say that you measure some length, and you say that that length is basically 16.5 millimeters, right? 16.5 millimeters. So there is a length which is 16.5 millimeters. So you have measured this, and you see, you're saying that it's 16.5 millimeters. Now, of course, you must have had some ruler, for example, and on your ruler basically gives you basically precision all the way up to the last millimeter, and then you have estimated this last digit here, and then you have basically report the value of this measurement as 16.5 millimeters. Now suppose that I want for some purpose I want to basically express this number in centimeters. So you know that basically 10 millimeters is the same thing as 1 centimeter, right? So I take this number as 16.5 millimeters and multiply it by, I use this as a conversion factor. I write 10 millimeters in the denominator and 1 centimeter in the numerator. Millimeter and millimeter I cancel out, and I divide this by 10, which gives me 1.65 centimeters, right? So as you can see, as I basically converted from millimeters to, and this is equal to 16.5 millimeters. So as you can see, as I converted from millimeters to centimeters, the decimal point moved 1 unit or one decimal point to the left, right? Because I had to divide by 10. Now let's say that you want to basically convert this value or this measurement again to a larger unit, for example to meters. Now you know that basically 100 centimeters is the same thing as 1 meter, right? So I write 1.65 centimeter, and I write it as 1.65 centimeter times, use this as a conversion factor, 100 centimeters and 1 meter here, and cancel these out, divide this by 100, I will get basically 0.0165 meter, right? So I have 6 and 1 and 2, so 0.0165 meters. So now as you can see, it's still the same number. I mean, it is still the same number that I started with, 16.5 millimeters, and this number has three significant figures. And well, this is again the same number. This is again the same number as this, meaning the value of this number is the same as the value of this number. So this also has, of course, this, if you count 1, 2, and 3, you have also 3 significant figures. 3 significant figures. And this number again has the exact same value as this number or this number. There is no difference between, for example, when you say 16.5 millimeters, that's the same thing as 1.65 centimeters, is the same thing as 0.0165 meters. The 3 numbers express the exact same length, right? So it makes sense that when you want to count the number of significant figures in this number, that you understand that basically, since the decimal point had to move to the left, for example, by 2 decimal places, that these zeros, first of all, this 0 is a 0 meaning that you can write the same number as 0.0165. You can write this number this way as well, and so you would lose that 0, which is not a problem. This is just to show that there is a decimal point here. Or you can write this number this way as well. You can put as many zeros as you want here, and it doesn't make any difference, right? So then what that means is that this 0 is just not important. You don't count it as the number of significant figures. And this 0 over here, originally we didn't actually have this 0 in the first place. We got this 0 because, well, the decimal point had to move back, and when you move your decimal point back, then of course you have to add zeros so that the number can be written. Otherwise, there is no other way to do it, right? So this number, this 0, is not counted as the significant digits or figures, and therefore this number has exactly three significant figures. So that is why basically, for example, when you have a number like, for example, 0.053, that the zeros over here are just not significant. It doesn't really matter how many zeros you have before this 5. If you had even 1,000 of them, it wouldn't really matter. You would still have two significant figures. And for these kinds of problems that we have with numbers, usually what we do is that we use basically some notation which is called scientific what do you call it? The scientific notation, I suppose, right? I don't remember the exact right numbers in scientific notation, right? So scientific notation, the name is, and so we, in order to get rid of these kinds of problems, we write numbers in scientific notation. Now, in scientific notation, what we do is that, well, the number is expressed as some number between, you have the form of the number is basically 8 times 10 raised to the power b, for example, where b is the exponent of 10 that you already know. For example, you could have times 10 raised to the power 12 times raised to the power 15 times raised to the power 3 times 10 raised to the power negative 15, and so on and so forth. And so that way you can basically express numbers very large or very small, and meaning that, for example, if you write, for example, I don't know, 3 into 10 raised to the power 30, you can imagine that you have a 3 over here and 30 zeros there. So you have 30 zeros in front of 3, which is of course very inconvenient. You wouldn't be able to even read the number, but you can just simply write it this way. Or you can say that if you have, for example, 3 into 10 raised to the power negative 30, what that means is that you have a 3, and then you have basically 29 zeros in front of 29 zeros before your 3. Then you have a decimal point here, and then you have a 0 here, and then over here you have 29 zeros here. 29 zeros here, right? So imagine that you can, using the scientific notation, you can express numbers that small. For example, the diameter of an atom, the diameter of a proton, neutron, and so on and so forth. And also you can, for example, I don't know, you can express the diameter of the earth, or diameter of the sun, or something like that. So using that notation, basically you can do this. So using the exponent of 10 serves to basically count numbers in front of some digit or before some digit. And then a is some number between 1 and 10, meaning that a is some number between 1 and 10. A is some number between 1 and 10. It's not supposed to be less than 1. It's not supposed to be greater than 10. That is scientific notation. Now, whatever number you have, yeah, you can convert it into scientific notation, meaning that if you have 16.5 millimeters, 16.5 millimeters, you can see that 16 is larger than 10, right? So I have to write this as 1.65 into 10 raised to the power 1 millimeter, right? So which is the same thing as 16.5, of course, but then you can see that this number over here is between 1 and 10. The value of this number is between 1 and 10, and then you have this base of 10 over here, and there is an exponent here, and your whole number looks something like this. On the other hand, if I had some number like 1.65 centimeters, 1.65 centimeters, so you can see that the number is actually written I mean the number itself is some number between 1 and 10. So then I can simply write it as, for example, 1.65 into 10 raised to the power 0. 10 raised to the power 0, as you know, is equal to 1 centimeter, which is of course not necessary. You wouldn't actually do this. When a number is 1.65, you just write it as 1.65. Or you could do it if you want to indicate that, for example, your number actually has 3 significant figures, meaning that when you write your number as 1.65 into 10 raised to the power 0 centimeter, what that means is that you're indicating that this number has exactly 3 significant figures. All the figures that you have there are significant, right? For that reason, you would do that. Or if you had, for example, some number like, for example, 0.0165 meter, 0.0165 meter. So again, you could write this number as this number has to be some number between 1 and 10. So I have to move this decimal point 1 and 2 places over to the right, which means that it gives me 1.65 into 10 raised to the power -2 meter. Meaning that you can imagine that if you multiply this number by 10 raised to the power -2, then this decimal point will jump over to the left by 2 decimal places, and you would get the same number, right? So that is scientific notation, and as you can see, in scientific notation, now you're indicating that this number has exactly the number of digits that you can count here are actually all significant, meaning that you have 3 significant figures here. You have 3 significant figures here. So that is basically that. Okay. That is basically that. So I don't know what I was talking about when I got here, but then now let's continue with this. Basically what we have here. We will actually continue the rest of this video in the next video, because we have already talked for 1 hour. We will continue this in the next video. Thank you, and I'll see you in the next video.